Okay, so whenever you have an airfoil and an airflow around your airfoil, there will be a non-symmetric pressure distribution. And so this shows a pretty typical pressure distribution for a typical airfoil. You see that you have the pressure drop is maximum here, which is where the flow acceleration is maximum. Anyways, let me just come down here. The pressure is a force per unit area. When integrated over a certain area, you get a net force. And if you do that around your airfoil, then you get the total net force acting on your airfoil. So the total aerodynamic force can be found by integrating the pressure distribution over the entire wing area. In the no-flow case, total aerodynamic force is 0, since pressure is the same everywhere and we have a closed surface. So you have a closed surface, you start integrating here and go all the way and come back to the point where you started. If the pressure distribution is the same, the integral will give you 0. But in the flow case, that's not the case. You have a changing pressure. So when the pressure distribution with flow is integrated, we get a total net force, since the distribution is not symmetric anymore. The total net force is a vector which has a magnitude, direction, and a point of application. Okay, so this is another critical point. So in reality, you have such a distributed force around the airfoil. Okay? Actually, instead of this, I think it makes more sense if I use this symbol. Okay, so every point on the wing surface is under pressure and contributes to the lift force. But if you integrate them all, if you do this integration, then in the end you get the total effect of all these distributed pressure forces, and that becomes a vector. Okay, so that becomes a force vector. And a vector means there's going to be several parameters forming a vector. This is a two-dimensional case, right? So when you're talking about an airfoil, you're looking at the two-dimensional picture. The third dimension, which is the span-wise direction, is not taken into account at this point. So the integral gives you a two-dimensional vector. So a two-dimensional vector will have two scalar components, right? And there is going to be a point of application. That's the third parameter. So the entire distributed pressure force can be presented by these three parameters. Okay. So this is an important step. So we go from here to here, and nothing really changes, because the effect of this single force is equal to the effect of this distributed pressure force. And in our calculation, instead of using the distributed pressure, we will be using this single force vector only, and nothing really changes, right? What's important is the entire force, and the entire force is the integral of that distributed force. So this is another simplification we do in our calculations to make, simpler equations, to study with simpler equations. We, instead of using the distributed pressure, we use this concentrated force vector. And we can represent these vectors in different ways, right? So we can use polar coordinates, for example. In polar coordinates, let me insert a new page to talk about that. Okay, so if you have a vector like that, you can represent this vector using its length. So this is our R vector. So let me call this length simple R without the arrow. and its angle. Let me call that theta. So these two can give you that vector, or you can use Cartesian coordinates, right? In that case, you define this axis system, and then you take the components along those axes. So you can represent this r vector using, let this be rx and let this be ry, or you can use rx plus ry to represent that single vector. In flight mechanics, we take the second approach. We use the Cartesian coordinates, and we define the axis relative to the free stream velocity. So the free stream direction is shown by this v infinity vector. So this is one of our axes, and we choose another axis perpendicular to that, and that becomes our second axis, and we talk about the components of the r vector in this axis system. And the component of the r vector in the direction parallel to v infinity is called the drag force, and the component perpendicular to that is called the lift force. Okay, so previously I talked about lift and drag forces. I said lift is to balance the weight, and there's also a drag force. You need a thrust force to overcome the drag force. And now here you see that lift and drag are actually coming from the same thing. So they are both coming from the distributed pressure, and the distributed pressure is represented using a single vector, and you divide this vector into two components, and the component parallel to flow is called the drag force, and the component perpendicular to that is your lift force. Okay? And then there's also the point of application. That also matters, where that force is applied, and that point is called the center of pressure. Okay, so here we say that it's the force is created here, and the force vector passing through here. So here, this picture is just to remind you that we're still talking about the two-dimensional case, but in reality, obviously, you have a three-dimensional aircraft. And the total force is obviously the force of all these forces on the entire wing surface. So if this is your airfoil, if you cut a slice at this point, then your resultant vector is somewhere here. But you can cut the slice at another span-wise location, and the other span-wise location will give you a different r vector. And if you do that for the entire wing, then you will have the entire lift distribution and drag distribution over the wing of the aircraft. Okay, so I'll be talking about this, but maybe I can skip that for now and then come back to that later. Okay, now let me talk about symmetric versus cambered airfoils. So here you can read through what I just said. Okay, now let's come back to the symmetric airfoils, where there's no camber. So what's special about this airfoil you see here is the upper surface is just a mirror image of the lower surface. And if such an airfoil is placed at 0° angle of attack, that means your V infinity vector is parallel to your chord line. in that case, the flow field will be symmetric as well, right? The flow flowing above the airfoil is symmetric with respect to the center line. So in this case, there will be no lift force, right? I think everybody will agree with this. If you have such a symmetric case, then the pressure distribution will be symmetric as well. In that case, the pressure on the upper surface is just a mirror image of the pressure on the lower surface. But still there will be a drag force. So that means the resultant force vector will be parallel. So this is your R vector. And there will be no vertical component. So lift is going to be equal to 0. And the entire resultant aerodynamic force becomes your drag force. So can everybody see why there will still be a drag force even though the lift force is 0? So let me try to draw a symmetric airfoil. It's not a very good one, but I think it's symmetric enough. Okay, so the pressure distribution will be symmetric. So this is our axis of symmetry. So whatever distribution you have on the upper surface, you will have the same. So let's see. By the way, I'm making this up completely. So the pressure will be the highest at the nose, right? That will be getting smaller. Again, I'm just making this up completely. And then the same pressure will be on the lower side as well. So in the vertical axis, everything will be symmetric and everything will be cancelling each other out. But in the horizontal axis, that's obviously not the case, really, because you have this flow coming towards your airfoil. This is your V infinity. And the nose of the leading edge of your airfoil is facing this flow. So obviously there will be the collisions due to air molecules at the leading edge, and that will create the drag force. And when you integrate, you get this resultant force. So here I define streamline. The path of a fluid particle in steady flow is called a streamline. Visible particles, smoke, are injected into flow in a wind tunnel to make streamlines visible. So these lines I've been drawing before. They are in fact called streamlines. Maybe I should have defined this earlier. But anyway, these white lines are called streamlines. And in a wind tunnel test, again, the smoke generators are used, and the smoke particles can be seen with a naked eye, and you can see the streamlines in a wind tunnel that way. So what we have here is there's a symmetric airfoil. This is the same airfoil as before, but there's a non-zero angle of attack. So your chord line is tilted. So this dashed line shows the chord line. And the flow is still coming horizontally. And now you have a non-zero angle of attack. And in fact, this is a positive angle of attack. And obviously, the flow pattern is not symmetric anymore. So in this case, there will be a vertical component as well. There will be a lift force. But well, it's already written here maybe, but so can you, by just intuition, tell me whether the lift force should be in the upward direction or in the downward direction in this positive angle of attack case? Up, right? Okay, good, I have that. So you're right. If you have a positive angle of attack, even though your airfoil is symmetric, there will still be an upward lift force. And by just looking at the picture, you already expect a vertical component because you don't have a symmetric flow field. But one way you can see this is such a shape, such an airfoil placed with a positive angle of attack will have an effect on the airflow, right? So your air is coming parallel to your to the horizontal, and your airfoil forces the air to be deflected, right? So when the flow leaving the airfoil, it will have a velocity that is slightly downwards, and that's because of the angle of your airfoil. Again, if you think about the Newton's laws of motion, by the way, please watch that video that I posted on Matthew Online, that MIT lecture. So he gives very nice examples of where these Newton's laws of motion are effective. So you have a flowing air, and your airfoil deflects that air, right? So the airflow will not be deflected by itself. So for you to be able to deflect that, you need to apply a force to it. And this is because of the second law of motion. And when the airfoil is deflected by getting this force from the airfoil, due to the third law, there will be a reaction to that. So the air will be applying the same force back at the airfoil. And the force that deflects the flow this way is in this direction, in that direction, and the reaction of that will be in the opposite direction, and this force is really your aerodynamic force, right? That becomes your aerodynamic force vector. So this is one way of looking at this lift force. Well, you can still do the other arguments where that there are pressure forces all around the surface, and you integrate them and you get the lift force. But this is a simpler way of looking at how these forces are created. When you deflect the flow, you need to apply a force to deflect the flow. And when you do that, the flow will apply the same force back at you, and that force will become your lift and drag forces. Okay? And in fact, I'm sure that you already experienced this before. And let me show you this video. I don't know if you ever did this, but I used to do this a lot as a kid. So if you do that, and especially if the car is going fast, you'll be feeling really strong forces. This can be dangerous. Please be careful if you try to do that. But I found this video yesterday, and when I was looking for that, I found some horrible news. You know, a kid's head got chopped off while he was trying to do that. It was really disturbing. And especially if you are driving yourself, then you should be extra careful. But if somebody else is driving, this could be a fun thing to do. So this is a pretty long video. There's no point in watching the entire thing. So if you try to, well, our hands are not perfectly symmetric, but you can assume it to be symmetric. So if you place it horizontally, it will be zero angle of attack, and there will be no significant vertical forces. But if you increase the angle of attack, and you'll start feeling the vertical force, and at some point it will be quite strong. And obviously, if you are driving really fast, then it will be much easier to observe these effects. Okay, now I come back to how control surfaces work, and they work based on the same principle. When you have a moving part at the trailing edge, that thing will deflect the airflow, and that's how you get force with a control surface. So you can read through this later on. But for the tail surfaces, well, the flaps work in a similar way as well. But this is the horizontal stabilizer. The entire thing is the horizontal stabilizer, and this moving part is called the elevator. By changing the elevator deflection, the pilot can control the direction of the force. So there will always be a drag force. You can't really get rid of that, but you can make the lift component or the vertical component upwards or downwards. So I'm not sure if you can still call it a lift if it's going downwards. Okay, so here's what I'm explaining why you need a horizontal stabilizer for a typical aircraft, for a commercial aircraft. Okay, so this is your main wing, airfoil. This represents the center of gravity of the entire aircraft. Okay, and you have a lift force. So maybe I should make a new drawing instead of trying to explain on this one. So this is your force vector, and let's say so this is our drag force and the lift force, okay? And your aircraft center of gravity is somewhere here. So this is the center of gravity of the aircraft, meaning the weight of the aircraft is in fact acting at that point. Okay, so you have this lift force here, and this is your central pressure. If you look at these forces, this aircraft will make a pitch-up motion, right? Because if you calculate the moment with respect to the center of gravity, the weight will have no moment because the moment arm is 0. But you have these lift and drag forces, and let's, for simplicity, slide this down a little bit so that the drag doesn't create a moment. Okay, so the drag force doesn't create a moment either because the moment arm is 0. But the lift force has some non-zero moment arm. And this will give you a pitch-up moment, right? So an aircraft like this cannot fly straight. It will be pitching up. And one way to fix this is you can make the center of pressure such that it coincides with the center of gravity. So if you can set center of gravity such that it is here, then you can keep flying straight because the pitching moment will be 0. But this is a very limiting condition, right? You cannot really make sure of that. Think about this aircraft, for example, here. While flying, the people on board will be walking back and forth, and that will be changing center of gravity. And you cannot make sure that center of gravity will be at a single point at all times. So what you do, you need an additional force to balance the pitching moment, and that additional force comes from your horizontal stabilizer. So if you have such small wing section at the end, you can use this to balance the pitching moment of the main lift force. And you can adjust the force here by using the elevator. So if the center of gravity changes during flight, if it comes here, that means the moment arm is greater, so you need a larger force to balance that, and you can make the force larger by setting the elevator angle here. Okay, so that's about that. So again, this is not really a nice drawing, but if you read through it, it explains what I'm trying to say here. So these are all supposed to be symmetric airfoils, even though it's hard to claim that. This is a symmetric airfoil at zero angle of attack, so the lift force is zero. If you have a positive angle of attack, then there will be a positive lift force here, and there will be some drag force. So a positive angle of attack gives you a positive lift force. And for symmetric airfoils, it turns out that the center of pressure is close to the chord point. So the C is your entire chord length, and the location of center of pressure is 1/4 of your chord length from the leading edge. So if this is the chord length is C, and this CP is close to 25% of the entire chord length from the leading edge. If you increase the angle of attack further, if alpha 2 is greater than alpha 1, which was already greater than 0, then the lift force will be increased, which is reasonable, I think, because you have a greater angle, and that will be causing a greater deflection in the flow, and that will give you a larger force. And but the important thing here is, even though the lift force changes, the location of center of pressure doesn't change. It stays at the chord-to-chord point. And this is just a property of symmetric airfoils, and I don't really have a convincing explanation for that right now. But when you take the aerodynamics course, hopefully you will be convinced that for symmetric surfaces, for thin symmetric surfaces, that's the case. If you have a very thick airfoil, then things may change. But for thin symmetric airfoils, this is true. The center of pressure stays at the chord-to-chord point. Okay? So this is a property of symmetric airfoils. Mm-hmm. Yeah. Well, there's a limit to this. I think that's what you're asking, right? So if you increase the angle of attack, lift force increases. But obviously, there's a limit to that. So let me use this to show that. So this is zero angle of attack. And when there's some angle, there's a force, because this will be deflecting the flow. But if I increase it more, then there will be a greater deflection and the force will be increased. But what's increasing is the total force, right? And at some point, the total force keeps increasing, but it will be contributing more to the drag force. And after a while, the increasing lift force will start going down. And obviously, at the limit, when your airfoil becomes perpendicular to the flow, in that case, there will be a huge drag force and pretty much no lift force at all. Um, that's true. Well, that condition is called stall condition, because the angle where the lift force reaches a maximum is called the stall condition, and if you increase the angle further, the lift force will start going down. Well, I will be talking more about that, the stall phenomena. Obviously, it depends on a lot of different factors. It depends on the airfoil shape, obviously, but it depends on other things as well. Okay. Now, let's talk about cambered airfoils. So, with the help of camber, flow rotation can be obtained even at 0° angle of attack. Well, here there's a positive angle of attack in this diagram. But even when the angle of attack is 0, you can get a non-zero lift force. That's not the case for symmetric airfoils. So, if a surface is designed to create force in one direction only, you use a cambered airfoil. It makes more sense. For example, the main wing. Let me come back here. This wing should create a positive lift force, right? So it makes more sense to use a cambered airfoil so that you can get a positive force even at low angles. But that's not the case for this one here. So depending on where the center of gravity is, sometimes you want a force in the upwards direction, sometimes you want a force in the downward direction. And for such a case, it's better to use a symmetric airfoil, and certainly for the vertical stabilizer. So vertical stabilizer serves a similar purpose. Sometimes you want a left force, sometimes you want a right force. But for the vertical stabilizer, you obviously use a symmetric airfoil. So if you look at the top view, so everything is symmetric with respect to the vertical axis, this axis, right? And obviously you use a symmetric airfoil for the vertical stabilizer as well. Now, on this page, well, these are supposed to be cambered airfoils. They don't really look any different than before. Probably I just copied these figures from the previous slide and called them cambered. Anyway, so this is obviously a cambered airfoil, and at 0° angle of attack, as I said before, you will get some positive lift force. And if you increase the angle of attack, just like before, the lift force will be increased up to a certain limit. So for mild angles of attack, this trend will be true as you increase the angle. So if alpha 2 is greater than alpha 1, then the corresponding lift force will be greater than the lift force for alpha 1. But what's important for the cambered airfoil is center of pressure is not fixed anymore. For a symmetric airfoil, center of pressure stays almost fixed at the chord-to-chord point, whereas for cambered airfoils, it's not the case. For low angles, the center of pressure is at the back, and sometimes it can be even behind the chord line. So your center of pressure can be greater than your chord length itself, and as the angle of attack increases, it gets closer to the chord-to-chord point. So here it's closer to the leading edge, as you see, and here it's even more closer, and the limit is still the quarter-chord point. It doesn't go ahead of the quarter-chord point. So this is an important difference between symmetric airfoils versus cambered airfoils. Okay, so the reason I'm telling you this is to study the entire motion of the aircraft. Knowing the lift and drag forces is very important, but knowing the center of pressure is just equally important, because without knowing the center of pressure, you can't really see the complete picture, right? Let me go back here. You know that your lift force should be strong enough to balance the weight, but if the center of pressure keeps changing, then you need to know that, so that well, you will need to balance that here. And while for symmetric airfoil, center of pressure is more or less fixed at the quarter-chord point, for the cambered airfoils that's not the case. For cambered airfoils, as the angle of attack changes, the center of pressure changes as well. Okay, so now I need to talk about this concept of moving the force to a fixed point, but perhaps I can wait until Friday before I start that. Okay, let me stop here, and I think you're tired already.